let me start with the unitary group U of n, unitary group U of n, and I will, can you see from this side? Do you see the whiteboard? Yes. From this side, do you see? Okay, so the unitary the unitary group. So then it is endowed with Haar measure, and I'm interested in the spectrum of the unitary matrix. So the spectrum of the unitary matrix lies on the unit circle. I have n eigenvalues. So, and the Haar measure becomes a measure on these eigenvalues. So the measure is the following. The measure is the following. Less than j from 1 to n. So then it is natural to consider the characteristic polynomial of this of my matrix. So this is image of Haar measure. Haar measure. Image of Haar measure on eigenvalues. Image of Haar measure on eigenvalues. So then it is possible to consider, it is natural to consider the characteristic polynomial of my matrix. Here it is. Characteristic polynomial of my matrix. And I'm interested in the behavior of the characteristic polynomial of my matrix as the format of the matrix, the size of the matrix, and n goes to infinity. This is the limit transition I'm interested in. So the the characteristic polynomial of unitary matrix of growing size. In fact, I will not consider this problem. It has been considered by many authors, and the results I present come from the conjecture of Fedorov and Keating. There has been a lot of work on this, but I will be interested not in this potential infinity, but in fact in actual infinity. I will take the limit transition immediately and consider the infinite particle systems, which is called the sign process. So, and the main role will be played in this discussion by the sign kernel, which is just the following simple kernel, Sxy sine pi x minus y over pi x minus y. So the sign kernel is the kernel of orthogonal projections onto the Pelley-Wiener space, onto the space of functions whose Fourier transform is supported in minus pi. So how is sign kernel related to this? In fact, it is possible to rewrite this formula. It's a simple exercise to rewrite this formula in the following way. This is the determinant of Kn theta j theta k d product. Well, I write like this, it's clear, product. So the main point is that the Dirichlet kernel, so this is just square of Andromont determinant, and rewriting it, one gets this determinant, where the Dirichlet kernel, theta prime, is, well, is in fact the Dirichlet kernel, sine n plus 1 over 2 theta minus theta prime over sine theta minus theta prime over 2. Here it is, the usual Dirichlet kernel. Now making, so Dirichlet kernel. Now making the scaling limit, taking the scaling limit, so let me write it in the following way. So the variable t, so let me explain the motivation for the scaling limit. In fact, when I consider the unitary group, I have n eigenvalues on a circle of length 2 pi. So the average distance between eigenvalues is 1 over 2 pi. So, excuse me, I misspoke, it's 2 pi over n. It's 2 pi over n. So the eigenvalues are very close. The eigenvalues are very close together. So I must expand my circle so that it becomes not the circle from minus pi to pi, but in fact from minus pi n to pi n, so that the average distance between eigenvalues becomes equal to 1. So, and this is precisely what is written. And under this scaling, it is immediate that the Dirichlet kernel converges to the sine kernel. And furthermore, it's a key remark that not only this measure has determinantal form. It's very nice that this measure has determinantal form. But the key point is that projections of this measure, this is not difficult, but it's also not obvious. The projections of this measure, so here maybe I have million eigenvalues, but let me project out all eigenvalues except 3. So I integrate over all of them except 3. Then the projection measure on 3 eigenvalues will also have the same determinantal form with the same determinant, of Kn, of the same kernel. Okay, so at least now everybody who can see and who can see better and who can see less well is in the same situation. Okay, so just the scaling limit gives us a system with infinitely many particles, which is called the sine process. So it's a system. The number of particles is now infinite, and the process, the measure, the Haar measure on unitary groups of growing size becomes, when n takes value infinity, becomes a measure on the space of infinite configurations of particles. So we consider infinite configurations of particles on the line. Ah, this is really nice. Okay, so now it's possible I can write. Thank you very much. So, and just this measure on infinite configurations of particles on the line is determined by its correlation functions, rho n, x1, xn, which in fact have, it is clear from what has been said so far about projections of this measure. So again, I consider projection of measure, let's say on million particles, but I consider projection on 3 particles. The million goes to infinity, but 3 stays the same. So the measure on 3 particles, it's still the same determinant. The kernel converges to the sine kernel. So this is exactly what I write. Determinant S, xi, xj. So the number of particles is infinite, but the so-called correlation functions, which are precisely the limits of these projection measures, the correlation functions are in fact just the same determinant. And this is the definition of the sine process. This is the definition of the sine process. Okay, sine process was introduced by Dyson, by Freeman Dyson. Okay, so now the object, the main object of this talk is the random, the analog of characteristic polynomial of this sign process. So the sign process, clearly it's not possible to consider polynomial of infinitely many with infinitely many roots. So the characteristic polynomial does not make sense. At the same time, the ratio of characteristic polynomials, so not the characteristic polynomial, it's not possible to take limit of polynomial with infinitely many roots, but the ratio of polynomials, this makes perfect sense, and this is a random entire function. So in fact, it's convenient for me to consider it as a function of two complex variables. So let me write this here. So I consider the function the product of z minus x over w minus x, where the product is taken over all particles of the sign process, it is taken in infinite value. So it is a random function, clearly of z, a random holomorphic function in z and in w. So in z it has 0 z point of x, in w it has poles. It's especially important to consider the particular case when w is equal to 0. So this is a random entire function of z. Here it is. Here it is. So and this is the analog of characteristic polynomial for infinitely many particles. So I'm interested now in the behavior of this characteristic polynomial, of this random entire function. And the main result of the talk, now I'm ready to formulate the main result of the talk. The main result of the talk is that this characteristic polynomial, this random entire function, converges to a random measure. So let me denote this. Let me denote this J, X, Z, W. Okay. So the main result is that Jx, so W has to be taken in the form Ri. Z is taken in the form I plus RT. So, and I take some power gamma of this quantity, I take absolute value of power gamma. I take expectation of this very same quantity. So, and this I consider, this expression, I consider as a random measure. Why random? Because x is random configuration. It's random infinite set of the line. So this is random measure on the line. T is in R. It's maybe convenient to consider T in 0, 1. It comes down essentially to the same. So, and the main result of the talk is that this measure converges, this random measure converges as R goes to infinity, converges to a very classical random measure, the Gaussian multiplicative chaos of Jean-Pierre Cahn, with parameter gamma. So the correlation kernel of this Gaussian multiplicative chaos is the standard one, this one, the standard one considered by Cahn himself, Jean-Pierre Cahn. I should say that the Gaussian multiplicative chaos has been constructed by Jean-Pierre Cahn, but in fact the problems leading to the construction of Gaussian multiplicative chaos stem from the work of Kolmogorov on turbulence, on turbulent cascades, and from the what is called the Kolmogorov-Obuchov conjecture, and also the reinterpretation of the Kolmogorov-Obuchov conjecture, which led to the work of Cahn, has been done by Mandelbrot and Perrier. Okay, so just this is the main result, and so I should say that here gamma is from 0 to 2, is from 0 to 2 0 and 2 excluded. The case of 2 is special. Please excuse me. The case of 2 is special, and this case of 2 gives critical case of 2. One needs case gamma equals 2 is special. One needs separate scaling square root of log r, and then the same expression, and it converges to critical Gaussian multiplicative case, critical GMC. So it's a little bit different. It's a little bit different case, but okay, let me not go into a lot of detail, a lot of technical details. It's just, let me say that it's a different case, but the result also holds with slight modification. I would like to emphasize the corollary of this result. So this result, what follows from this result? Let me write this. Okay. So, okay, if there are any questions concerning the main result, maybe it's good to ask them, because now I will erase and pass to corollary. So if maybe... No. Thank you very much. This is a very good question. And just precisely no, because there are no martingale. This is very important to emphasize. In fact, the approach of Jean-Pierre Cahn and of several followers of Jean-Pierre Cahn rely on martingale properties. Cahn considered Gaussian processes and convergence of Gaussian process and of exponential of Gaussian process to this random measure. Of course, when one has a Gaussian process, then there are many natural associated martingales, and Cahn takes full advantage of this. But in fact, no. So here there are no martingales. So because my random variables, they're not Gaussian, they're asymptotically Gaussian, they're not Gaussian. I will say this in a moment. But my point is that the, how to explain myself, the approach that works is the approach suggested by Nathaniel Berestitsky in Vienna. So Nathaniel Berestitsky, his approach is, maybe it's possible to say, elementary. It's purely L2 approach, and in fact, the approach of Berestitsky is based on theorem of Girsanov. So theorem of Girsanov, theorem of Girsanov. Of course, it only holds in Gaussian case, but so to speak, approximately. How to say? Of course, Girsanov theorem does not hold in non-Gaussian case. It's also specifically Gaussian result. But I need only small piece of Girsanov theorem, which also holds in approximately Gaussian case. So just the idea of Berestitsky is the idea of some smart cutoffs of just L2 convergence. I say just one last technical thing, and then I go back to non-technical exposition. The key difficulty in proving such results is that their L2 convergence does not hold. So, in fact, L2 convergence does not hold because there are parasitical heavy tails, which one needs to cut off. And so Berestitsky cuts off these heavy tails using Girsanov theorem, but in fact, one does not need Girsanov theorem in its full force. So for cutting off heavy tails by Berestitsky method, full Gaussianity is in fact not necessary. Just approximate Gaussianity is enough. Okay, so let me first formulate the corollary and then explain where Gaussianity comes from, and then maybe conclude. So a corollary is the following. So as I started with discussing the unitary group. So the unitary group, and let us go back to the unitary group. And of course, if I have the unitary group, so the chairman is not here, so I keep talking because you don't stop me. Okay. So I consider the unitary group, and just the Dirichlet kernel with which we started is kernel of projection on clearly n harmonics. So this is projection on trigonometric polynomials of degree n. So it is, please observe that the measure, the Haar measure on eigenvalues, is measure on n particle configurations. So n particle configurations. N particle configurations. N particle configurations. So it is clear that a polynomial of degree n, so polynomial, oh, okay, n should be the same. Polynomials of degree n are uniquely determined. Polynomials of degree, not n, but n minus 1, excuse me, of degree n minus 1. Polynomials of degree n minus 1 are uniquely determined by their n values. So values at n points uniquely determine a polynomial of degree at most n minus 1. So there are n parameters, and so values at n points uniquely determined. So there is the following simple observation, that every realization of my process, so n particle configuration, is uniqueness set for the range of this kernel, because the range of this kernel is the set of polynomials of degree n minus 1. So in particular, if a polynomial of degree n minus 1 is zero, is zero at these n points, then it is the zero polynomial. And on the other hand, for any subset of these n points, so I take all points except 1, there exists a non-trivial polynomial which is zero at all points except 1. So it's what's called minimal uniqueness set. Minimal uniqueness set. Minimal uniqueness set. Minimal uniqueness set. Okay, so what happens to this property when we take the scaling limit? What happens to this property when we take the scaling limit? Well, let us see. So, in fact, there is general result which we proved with my co-authors Yan Titu from France and China, and Alexander Shamov from the Ukraine and Israel. So, just the result, we proved that for any determinantal point process, almost every configuration is a uniqueness set. Almost every configuration is a uniqueness set. So the uniqueness part is just completely general result. So for any process whose correlation functions are given by determinants with any kernel, the resulting configuration is in fact a uniqueness set. So a function from the range of the kernel which is zero on the configuration is in fact the zero function. Okay, so okay. Now the question is it a minimal uniqueness set? Is it minimal? Is it minimal? So here in the finite dimensional case, it's a uniqueness set, but it's also a minimal uniqueness set. I should say that our joint work with Xiu and Shamov builds on previous work of Lyons and Ghosh. So, okay, so is it minimal? And quite surprisingly, the answer is no. So in infinite dimensional situation, it is not minimal. And in fact, a result, and by the way, it's in the preprint, which is on the archive, is that the sign process has access 1. Has access 1. Has access 1. So what do I mean by saying that the sign process has access 1? so that almost every realization of the sign process becomes minimal uniqueness set, if one particle is removed. So if one particle is removed from the configuration, then the resulting set without one particle is in fact a minimal uniqueness set. Then the resulting set is minimal. The resulting set is minimal. Is still a uniqueness set, is a minimal uniqueness set. So it's important to realize that is a minimal uniqueness set. So it's important to realize that just not every uniqueness set contains a minimal subset. So we are used from linear algebra that if there is some set in a linear space, then if it's a uniqueness set in linear space, then there is one can choose a basis out of it. But it's not true here. It's not true here. It's possible to have a uniqueness set out of which one cannot extract a basis. One cannot possibly extract a basis. So just here, it's not just the question of computation of this access, it's also the question that this access in fact exists. So why is there this extra particle? Why is there this extra particle? This extra particle is there precisely because of the random measure. So the random entire function, that I wrote, in fact does not, cannot possibly be a square integrable function because it converges to random measure. So if it converges to non-trivial random measure, then its Hilbert norm in fact grows. But this is precisely why, very informally, the reason why the sign process has access 1. So if I remove some multiples from this product, then I arrive at L2 function. Okay, so I draw to conclusion, and just let me just very briefly say that the Gaussianity of this whole setup is based on the theorem of Soshnikov. So on the theorem of Soshnikov, which says that if I consider additive functional of the sign process, so if I consider SF, which is the sum of f of x over configurations of the sign process, then the Soshnikov theorem, very nice. Okay, so then it's important that mathematical theorems, they should somehow throw light on a subject. So just Soshnikov theorem, it says that if f takes the form, is chosen the form like this, is extended by a factor of r, then SF of r converges to the normal distribution. So please observe that the key point here is that this convergence takes place without any scaling. It's absolutely key point. It takes place without any scaling. The variance, this is very beautiful. The variance is the, well, 1 over 4 pi square is the Sobolev 1/2 norm, 1/2 semi-norm of of the function f. Let us recall that the Sobolev 1/2 semi-norm of the function is just the integral of the square of the Fourier transform times lambda. Here it is. So, and then it is taking, so to speak, the exponential in the Soshnikov theorem that that allows one to conclude the proof of the result. So in fact, the sum, so not just the sums converge to the normal distributions, but in fact the exponential of the sums converge to the exponential, which is indeed the Gaussian multiplicative chaos. And so the key point in the argument, the key difficulty technically is just the taking the exponential in the Soshnikov central limit theorem. Okay, and just one last remark that I want to make is that the key point that allows one to take the exponential is, I will not even write it down, I will just say, is in fact on what Soshnikov theorem is based, is in fact the second theorem of Sigot. The second theorem of Sigot in the form of Borodino-Kunkov. So the second theorem of Sigot, Borodino-Kunkov-Geronimo case. Kunkov-Geronimo case. So the second theorem of Sigot is an asymptotic for Toeplitz determinants. So in this asymptotic, it is possible to take scaling limits. So precisely, asymptotic of Toeplitz determinants works for the unitary group itself. But here it is necessary to work not with the unitary group itself, but with its scaling limit. Okay, so it is not possible to apply directly the second theorem of Sigot. It is not possible to apply it directly because it itself is a limit relation. So then there becomes a question of two limits. But the formula of Borodino-Kunkov-Geronimo case is the second theorem of Sigot with error term. And in the theorem of Sigot with error term, it is possible to go to the scaling limit. And this is exactly a key point, a key step in the argument. And taking, by the way, I should say that the theorem of Sigot admits of very precise version due to Ibragimov. And just this result, I don't know, so this is an open question. I think for this result, I don't know. So Ibragimov's theorem, it is, how to say, it is a precise version. It's an if and only if. It's precise version. It sets precise boundaries for Sigot theorem. For this result, I don't know Ibragimov type result. I think it's a very interesting problem to obtain Ibragimov type result in this formula because Borodino-Kunkov they do not aim for precise generality. They just give some sufficient condition. It's enough for me. The sufficient conditions they give, it's enough for me. I take scaling limit, it's quite enough for me. But still, it will be interesting, obviously, to obtain necessary and sufficient condition in Borodino-Kunkov formula. In any event, using the Borodino-Kunkov formula, it is possible to take exponentials to estimate quite precisely the exponential moments of these additive functionals, which is to say, to estimate the precisely to give estimates for the random entire function with which we started. So here it is. I just write it again. So which is to say, to obtain the convergence of Gx I plus RT Ri over to the power gamma over the exponential of the same to the Gaussian multiplicative chaos. So this is the main result of the talk, and from which one obtains the corollary that the sign process has axis 1. Thank you so very much.
Thank you.